Mr. Ken Hicks came from Oklahoma and to New England to learn the craft of furniture making, and from a British furniture maker named David Powell. And after mastering that art of furniture making, he moved, thankfully for us, to buildings, and first in residential and commercial properties. And today, his portfolio includes hundreds of beautiful, energy efficient, new and renovated, both sides of the equation, as well as authentic historic restorations. Some of you have been through Old Deerfield, might have seen some of his, or would have seen some of his work. So over that journey, his commitment to mitigating climate change and his passion to learn the best practices in building science have made him the innovative leader in the construction of high-performance building that he is today. And his presentation today is going to inform us of his journey to where he is presently, himself personally, and his company. So I am especially pleased to introduce an individual whose construction practices represent an exemplar to all of us. So please welcome Ken Hicks.
Thanks, Carl. So I've got a lot to get through. So if there's any burning questions, go ahead and ask. But otherwise, we might save it till the end. Any questions about what this is? Just to start, we're all clear. Net zero energy retrofits. So let's move through. And this is about shelter, really. And I'm going to tell you my journey. It'll be really quick. I'll go right through it. I started as a framing contractor, was a framing carpenter. Before, during, and after college. And believe it or not, what I built was way worse than what you see up here. And then I changed careers for a while, and I lived in wilderness areas for a few years, and I lived in shelters like this. And I learned a lot about how to keep warm and how much stuff you need to put between you and the ground or you and the outdoors. And learned that as long as you stay reasonably warm and somewhat dry, you can survive just about anything. These shelters were pretty good down about 15 degrees. When I came east to study fine furniture making with David Powell and Elon Tierney's dad, John Tierney, after I completed my time with them, I went back into building and designed houses like these. These are a few of the houses we built. Now, the only good thing I'll say about these houses, they store a lot of carbon. That means we put a lot of wood into these buildings because we wanted to make them really strong. We weren't thinking about insulating, in 1982 so much as we were thinking about let's keep these houses from blowing away. And I think that's still something we face in the building industry, is a challenge of changing how we build buildings. This is really a part of the fabric of being a builder, is building something really strong. There were no design awards won in building these buildings, I will tell you that, but they still look pretty good. 25 years ago, we moved to building what were called energy crafted homes. This was a program that was just a little bit ahead of its time. We were building double stud walls, exterior insulation, blower door test, a lot of ground source heat pumps. What else? Let's see, ventilation systems. So it was a lot of stuff 25 years ago that we're still using today. And so it was a great program. And about 12 years ago, I met Katrine Klingenberg, who brought Passivhaus into the United States from Germany. And was just very excited. Long conversation with Katrine in Boston, and became one of the first certified Passivhaus consultants in the U.S. So these are some Passivhaus buildings we've built, some we've designed, some we've worked with the local architects on. And so that what we do a lot with Passivhaus is we call them Passivhaus aligned. A lot of times we don't certify because it's an extra cost to get the certification. So that's what these are. So you've all probably seen the hockey stick of CO2 emissions going up from Industrial Revolution, kind of. And this is what we think about every day when we get up, when we come to work. What CO2 or CO equivalent greenhouse gas in the atmosphere. And it informs our decisions every day and how we think about the buildings we built and what we should be prioritizing. So this is a wonderful graph I pulled off of a blog that I think says it all where we are in this world. We're in that sweet spot of today between when it was 5 degrees Celsius cooler, we were under half a mile of ice where you guys are sitting today. If it's 5 degrees Celsius warmer, we're in big trouble. So this is why we think about this every day in our work. Where are we now is the question. So our average cost to build net zero is around $250 a square foot. And that's pretty good for a net zero average cost. Yeah. Our average cost. Yeah. But that's not affordable for everybody. And this is where we feel like we have to kind of rework what we do. How can we make this more affordable? Because really, our goal is everybody who's building a new home should be able to build to net zero or net zero ready, meaning you put a few solar panels on, you could get to net zero. And so where we want to be is $180 to $200 a square foot. That's our goal in net zero kind of passive house aligned buildings. What we're not going to do is build a house to code and put a ton of PV panels in the field or on the house or whatever buildings we can do. We feel like PV is great. I mean, it's renewables, or it's a great part of the solution where we need to go and to lower that greenhouse gas emissions. But we need to build our buildings right to start with. We work on buildings that are 200-300 years old all the time. If buildings are taken care of, they can last a very long time. Whereas renewables, PV, have a much shorter lifespan. So we're not going to build a house to code and throw 15 kW in the field. We just don't feel it's the right thing to do. So that's where we start with. We're not going to do that. So when we got into Passive House, a good friend of mine named Mark Rosenbaum, who's an engineer, and Mark and I met 25 years ago when we were building energy crafted homes. And Mark and I were talking one day about what is Passive House. And does everybody know what Passive House is? You all kind of familiar with it? So basically Mark says, Passive House is the energy efficiency dial turned up to 11. Let's just pull out the stops. We're going to be super energy efficient. Forget everything else. This is about efficiency. And so for us, we felt like there's got to be more to it than just efficiency. We need to make it affordable, our buildings. We need to hit that $180 to $200 a square foot. We need to make our buildings healthy. We spend, in the United States, our average lifespan 79 years. We spend 70 years indoors. That's a lot, right? So what kind of environment are we living in every day? We need to really think about stuff we put in our houses, how we build our buildings. It's an ongoing kind of, can we do better? Are we bringing the right things in here? And low embodied carbon, which I'll dig into a little bit more. And basically low embodied carbon is also kind of referred to it's material extraction from the earth, whether it's wood or rock or whatever it is. It's manufacturing, it's transportation, it's bringing the material to the site. It's how much went into building that building. What were the carbon emissions that were emitted in the building of that building? And so the reason that is so important is because when you get the load of a home down so low, that carbon emissions of what it took to build a building is really a big part of the whole calculation. So these are the four main dials that we are looking to turn. We can't turn any of those up to 11. If we turn one up to 11, something else has got to go down to a 5 or a 6. But we want to turn them all to an 8, and that's our goal. So if we look at the efficiency, we look at Passive House as our kind of gold standard. But a lot of Passive House, and the reason it really appealed to me when I met Katrine was it's stuff we already do. We just need to do it a whole lot better. It's super insulate the house, air seal the house, good ventilation strategy, take advantage of solar heat gained, and high performance windows. So it's really a really good healthy package of the way to build. We want to eliminate all air leakage, and when we're starting building Passive House, we used the PHP, the energy modeling tool, pretty much exclusively. And so this is a great tool to use. It's about 34-page spreadsheet. It's pretty intense. It takes a long time to get it done. Now there's what in the US there's what's called Wolfie Passive, which also analyzes the moisture flow in the wall systems. We'll talk about a little bit about that later. And so we want to determine our air barriers, how they're all going to tie together. We want to do a thermal bridging analysis of our assembly. So I don't know if you've ever run therm, anybody run therm in here? It's a pain. So the best thing you could do is just not have any thermal bridging if you're going to try to certify Passivhaus, because running a therm model is kind of because you got to relearn it and it just takes forever. We want to get the shading right. We want to get the amount of glazing right. And we want to remove all combustible appliances. Right. So, and we want everything to be electric if we can, if we're going to try to hit net zero with our PV panels. So in this case, we use a lot of the wall-mounted mini splits. You've probably seen these around campus. We use a lot of these ceiling mount units now. And the great thing is they're modifying these, and they're much less intrusive. They more of the rectangular shape as the wall-mounted unit, and they're very, a lot of people don't want to see that on the wall. So we go to the ceiling cassettes, and they work great. The other thing we do a lot of are ducted systems, so you don't see any of it, but it's more expensive to get there. We're not going to get to $180 to $200 with a ducted system. That's why if we can get a point source system, that's what we want to install. This is one that's not taken into account near enough, is hot water distribution. So the reason is, for a really energy efficient home, up to 25% of your energy use is going to be around with your hot water. So we want to think about where our hot water heater is located, what the distribution is. We want our hot water to get to its source within seconds, not minutes, as a lot of homes that you've probably seen. You're waiting for hot water and standing there. So that's a big energy draw on the houses. So we want to centrally locate that hot water tank. We use a lot. This one is not. We use a lot of heat pump hot water heaters, which are great, very efficient. And then finally, we want our blower door to hit between 0.2 and 0.4 ACH 50. So these are the standards of efficiency that we want to hit. And we can hit these easily because we've done it a lot and we know how to do it efficiently. And that's the key, is efficiency of putting all of this together. We want our buildings to be healthy. As I said, 70 years indoors. Good ventilation strategy is really important. We use this manufacturer a lot. It's a company called Zender. They're from Germany. The great thing about this ventilation strategy is all of these lines go to exact point source of distribution or extraction. So there's not kind of an open volume. You're hoping it all works. And when we think about ventilation, we're thinking about the health of the occupants, because does everybody understand how the core of this works? I can explain it a little bit if you're unclear, but I'll just go over it quickly. So So the extracted air from the house comes through this chamber. It's kind of a heat exchanger. The outside air comes in, whether it's cool or hot out, and it's acclimated to the indoor temperature and then distributed. So you don't get, 20-degree air blowing on you inside the house. We try to when this is distributed through these are basically 3-inch, and they're just like vacuum cleaner lines. So when they're distributed, we put them in the bedrooms and all the living spaces. So we put them in a place where it's not blowing right on top of you. It's not over your bed, so you won't even know it's running. It runs at a very low speed. So it's this is a great application for this ventilation system. Now, we use the ERVs. You can use energy recovery ventilators or heat recovery ventilators. So we use all energy recovery ventilators. And if you look at the maps, and this is something I want to talk about a little bit too, is how fast all of this is changing as we get more data. And it's really important to keep up with the latest maps, and the data's coming in, and we're really on top of monitoring all of these systems. So the energy recovery ventilator we like for New England, because it in the wintertime, it doesn't take out all of the moisture of the house. So, it gets, I was noticing today a bit of static electricity around here. So it gets really dry. I'm wondering, what the average RH in here is, Carl? Yeah. Yeah. So we try to hit 40 as a minimum, hopefully more around 45% RH is what our goal is. So the ERV doesn't take all of that moisture, just doesn't suck everything out of the building like the HRV does. And the other thing it does in the summertime, we have more humid air outside. It doesn't bring that humid air into the house as much. And it's a much lower load operating system. In defrost mode, it doesn't take as much energy. So ERV is pretty much all we use exclusively now. So we really want to think about how this building is going to be lived in. And that's why we like to distribute fresh air to the bedrooms. So as the daughter of teenagers at one time, we know how hard they're able to get them up out of bed. Well, when you have 1,000, 1,200 parts per million of CO2, it's even harder. So we try to maintain 600 parts per million or less in the bedroom. So it's really important. It also is very important for health. Just, keeps out sickness, respiratory illnesses, if you can keep a safe level of CO2. So the thing we love about this particular system also is it's easy to balance the ventilation. So this, that was Mike, as you saw in an earlier slide. So this little disc on the port turns so we can balance the flow of the ventilation in the house. So we want an evenly balanced ventilation system. You want the same amount of exhaust air as the amount of supply air. That's really critical to how things are going to perform. Otherwise, you're just kind of hoping that it's going to where it's supposed to be. Now, I will say that architects, builders, your future engineers, architects, it's important that your HVAC contractor understands that these systems need to be balanced. It's a lot of I think this will work okay, but you can test it. You can balance your ventilation in any system. We just like the Zender because it's much easier to balance. But if it's an open floor plan, it's, then we're not supplying every room with this type of air. Undercut your doors a little bit. If it's an open floor plan, you can keep that CO2 level in a safe range. The other thing we do is, early version of Passivhaus, we were not venting the hood vents. We were putting charcoal filter vents in because it was a big push on let's not put another penetration through the building. And that's what a stove hood vent does, right? So, but of all the research we've done and working with our colleagues, we realize now that we need to get that particulate matter out of the building, out of that space. That is a definite long-term detrimental health effect, is particulate matter in the air. So we're going to take the energy hit and we're going to vent it out of the space. So, and we're also going to use take all combustible appliances out of the building. So that takes the life safety issue out of it. When we have which we have put in kitchens where they want, the massive 1,200, 1,500 CFM, vent hood, and it's going to get to negative pressure really fast with that because there's no air to make up as you're blowing it all out of the building, then we'll install this makeup air system. So the way we wire it is all you have to do is turn on your hood vent. It comes on. You don't even know it's running. We dump that air because it's still not quite up to temperature of the inside of the house. We'll dump it like behind the refrigerator in a grill. So by the time it reaches that kitchen, you won't even know it's coming in from the outside. It'll be up to room temperature. So if it's a very small house, we'll use that. If it's like I say, a massive hood vent, we'll use this. Worst case scenario is if you don't have one, you just crack a window, right? If you have combustible appliances, you may have to be worried about what's going to happen. Or if you have an open fireplace or a wood stove in the house, then you're going to pull that smoke right into the building. It's not a pleasant experience when that happens. So, but that is about a $2,500 upcharge. So it's a little harder to hit we're still thinking that 180 to 200. So we're telling people, use a little bit of management and if you don't get any draw, just crack your window a little bit. So the other thing that we do a lot of are, we do put a lot of wood stoves in, but we try to get it out of the conditioned envelope if we can. And again, for the reason of not drawing that smoke into the building. Although we also have put a number of wood stoves inside the building because people want that safety of, what if the grid goes down? What if the power goes out for a week? You know, I got to have heat, right? So that's fine, but we say you got to splurge. You got to spend a bit more to get a really airtight wood stove in your house if that's what you're going to do. The irony is, of all these we've put in, nobody has lit it yet, and this is years now. So the houses are very comfortable, and we take advantage of that solar heat gain. So even when we, this house here, I'll just tell you an example. This is this house. You can see on the left, that's that wood stove. So this is actually a 4-season room. So they've got glass panels that go in here. But so in this house, when it got, I think it was 10 below a few days last year, they just wanted to do an experiment to see if this stuff really works. So they shut off the heat for 3 days, and it dropped 2 degrees in the house. So if you design it right, it works. So take advantage of the solar heat gain. The other thing we really pay attention to, and I get this beat in my head by Joe Stebrick going to his classes in summer camp for 20-something years, was the building science of walls and roofs and assemblies. And it's the stuff you don't see that can kill you, right? Well, it's not going to kill you, but it can make you sick. So if you're not careful with how you build your walls, and I see examples in Carl's room, I know y'all are working on this, is your walls got to be able to dry out. That's the key, right? So walls, roofs, there's going to be a moisture drive that occurs over the seasons. It's just natural, and that's okay. And as long as it dries, then you're fine. It's when it doesn't that you're going to have problems, and you're not going to know about it until somebody's just not feeling well is the problem. So we take the building science part of our buildings really seriously and how these go together. And we want our HVAC installers and our insulators to understand the science behind it too. So they may see things that we're not if they're paying attention. So we monitor, or we have monitored, we're not doing it as much anymore, these different assemblies. So when we're pushing the envelope of what's possible, how much insulation should you be putting in buildings, we modeled it in something called WOFE, which is a moisture analysis kind of model, and on that drive of wetting and drying. Like I said, as long you can get up to 20%, 22% moisture content, as long as it doesn't stay there very long and it drops. So that's the key. So this allowed us to see this in real time. So we put these little sensors. This is about the size of a matchbox, and it picks up. There's screws that go into the surface that we want to test. So it picks up relative humidity, moisture content, temperature, and I think actual humidity. So, and then this little antenna sends a signal to this gateway, which is in the mechanical room, and then we can go online and we can watch this in real time. And it's incredible how things will wet and dry, and just year to year you can watch this cycle. It's pretty amazing how consistent it is. More about the health is we refer to the red list a lot. You're probably familiar with this, and we were just talking about this in our office this morning. We're getting ready to use this product, and we said, has anybody checked the red list on this yet? Even though it's an exterior product, we also want to think about what we're exposing our workers to, our employees and our field crew. The Declare label is great. Green Guard label is great. There's more coming online that I think are going to be equally of value, but these are the main kind of go-to labeling that we use right now. So, and then just stuff local. Natural Vermont Coatings is great. We use this all the time. We're getting ready to do a whole interior with this product. This the Ben Moore low and zero VOC products. And then we're done. Then it's up to the homeowner. Now, what they bring in the house, we can't control, but we can try to help educate them and understand that what they bring in has probably got formaldehyde in it, and it's got chemicals that aren't good to bring in a space like this. Now, the good thing is we're constantly ventilating the house. We're constantly changing the air in the house, right? And the great thing about that that core is it's also filtering the outside contaminants before it comes into the house, the allergens. And, if you got something like this, it's near a highway, it takes out that particulate matter. But what comes into the house, we can't control. We can just advise. So we advise people to get some really good monitoring equipment if they really care about the well-being of their family and keep an eye on things so they can see what's happening. And it's interesting. A lot of folks want to do their CO2 monitors now too and just set it up in the bedroom, make sure their kids, we're hitting around 600 parts per million or less, preferably. Let's talk about embodied carbon dial. And so last year, this book came out called The New Carbon Architecture. And it was, it's a great book. I recommend everybody reading it. It's about what's going on now. It's about the future. It's about materials we could and should be using. And I'll talk more about that later, but this is one to read. And we were at NESE conference, Northeast Sustainable Energy Association conference last year, and the open plenary was great. It was about farm to building. And this is super exciting where things could go with this. With hemp, with straw bale, with mycelium, with earth block, with earth floors, and this whole idea of we're sequestering carbon in this plant-based material, and then we're putting it in our buildings and storing it is really incredible. We're not there. I'm leaving it to the younger folks in our company to drive this forward because it isn't where we need to be going. We're looking at a possible project to use earth bricks. We may be using that on another project overseas. So we're excited about this technology and what we can do with it. So concrete, oh man, this is a hard one. Huge embodied carbon in concrete. In the process of creating clinker, we know that decarbonizing limestone is a huge energy hit as far as CO2 in the atmosphere. So there's not a whole lot we can do about it except use less of it and look to use substitute materials like the rammed earth or the earth block whenever we can, or just when we do have to use it, design it, minimize it. Now we can talk to our suppliers and say, what's the percentage of fly ash you're using? What's the percentage of blast furnace slag or using any ground ball of glass? And that's a fairly new technology that's still being developed. And there's issues with it, like any new technology. But there's a lot of it. A ton of cement is a ton of CO2 in the atmosphere. It's big time. It's a problem. But there are things that we can do now. Like all of this is great. The hemp, straw, rammed earth, this is all great. But what can we do now? And there's a lot we can do. We can use advanced framing techniques. And this is a hard one to get. So we have a lot of framing crews that work with us, and we have to continuously ask them, please don't put all of this wood in this house. You don't need that much, So we'll do really detailed diagrams of how walls should be framed. And that way, we're taking out the waste from the beginning. We're not, they don't have to think about how their layouts are going to work. We're going to lay it out for them. So, but we can start with just dematerializing the building. There's too much waste in every trade. Fortunately, our cellulose installers that's not that bad, but use dense packed cellulose. That's just, it's a great product. It's a recycled product. We use it in all our buildings. So there's a lot of talk about global warming potential of product, and I don't know if everybody knows what that is, but it's really important to know. I mean, you don't have to, if you want to dig into all of the meaning behind it, it's great to understand all of this. But basically, when you get a product like a foam or a refrigerant or whatever, and it's a certain rating of a GWP, global warming potential, if it's 100, if it's 500, if it's 1,000, what that is relation to carbon, relation to CO2, carbon dioxide. So that's, if CO2 is a 1 and your foam is a 100, it's 100 times worse is basically the idea. So it gives you some perspective on the products you're using when you look at the GWP of material. So there are products now that we can make decisions about. and one of it's foam, and this is really goes to how fast this industry is changing, is that, we saw foam as this great salvation not that long ago of, man, this is high R value and it's great. But now it's hydrofluorocarbon, and it's not great material. It's really bad for the environment. Well, and I'll talk a little bit about that, but we have choices now though. So the XPS foam, you see it, all the lumber yards carry it. We should be using EPS instead, the white stuff, instead of the pink and the blue stuff, although XPS is changing. I don't know that they're there yet. Do you, Ben? I don't know if it's completely switched over yet, but yeah, it's a slow ship. Again, Dow, Owens Corning, if they're saying we're going to lose our R value, we're not in any hurry to do this. Well, it's already mandated in Europe, so we're hoping that it'll hit the US. This is a big one that architects can spec out of their drawings, like do not use HFC-based spray foam. Most insulation companies still are using HFC-based spray foam. So HFC, I'll just real quick background. Y'all remember, well, y'all probably too young for this, but there was a big hole opening up in the ozone layer, and it was from chlorofluorocarbon, and they realized that it was really bad stuff, and it was used in refrigerants at the time also. So the really cool thing about that is it only took 2 years to identify what the problem was, fix it, and fix it globally. So it was banned globally in 2 years. Like, we know we're up against it here, but man, that gives me hope that we can come together on some of this stuff. But they replaced it with hydrofluorocarbon, this product. So the good thing is that doesn't eat the ozone. The bad thing, it's like thousands of times worse than the CO2 equivalent. So instead of 1 GWP, and when it's used in refrigerant, it's thousands of GWP. So in spray foam, it's less. But we have a choice now, and it's some of the spray foam has moved over to hydrofluoroolefins. So that has a GWP of 1, but most of the installers are still using, I don't have to get too confused here, are still using the HFC-based spray foam. So, and it was interesting reading back on this and looking at, you look at old comments online, and it wasn't that long ago that said hydrofluoroolefins will never match what HFCs are doing. It's too expensive. The R value is never going to get there. Well, it's here. It's practically the same R value, just pennies more than the HFC-based. So nobody should be spraying HFC-based spray foam anymore. Now, there's still issues with HFO, with hydrofluoroolefins, but it's a whole lot less than HFC. And the best thing is try not to use it at all, spray foam. If we can use it with other materials, with cellulose, and so when we do use it occasionally, but we try to use it minimally. And it's still a really good product in retrofits. It's a hard one to lose in retrofits. That's the rub with it. But you can get the HFO based. That's my bandwagon on foam. So, and how do we make all this affordable? That's the tough dial. So we've built about any structure of wall that you can imagine. Exterior Larson truss, double stud wall. This is 6 inches of exterior polyiso strapped with a basic rain screen attached. 6 inches of, this is the beginning, what ended up to be 6 inches of 8-pound density rock wool. So what's the most effective, efficient way of building residential single-family homes? So that's what we needed to decide if we're going to hit the affordable dial. And so we had an intern from UMass, Dylan, and I don't remember his last name. Dylan, I don't think so. I don't think it was. Anyway, he was great. What you all are doing here, I don't know what you're doing with these folks, but he was really a really great guy. So we said to Dylan, here's the puzzle, Dylan, is we want to figure out what wall system is the lowest embodied carbon, is the least cost, and the most efficient. Small task. Figure it out for us, right? So he went to work use the Athena impact estimating modeling. I'm not going to go through all the details. It'll take forever to get through this. But I said I gave him 11 wall assemblies to build. I said, Dylan, here are some of the wall assemblies we built. Now, I've got a pretty good idea what's the right choice, but it would just be pulling it out of the air, and that's not a very good way to do things. So he dug into all 11 of these, and he looked at the embodied carbon testing and extraction all the way, so basically cradle to cradle, or actually, yeah, cradle to cradle, because he went through recycling. Looked at the cost calculations for all of these assemblies, put all the data together, looked at where we're getting the resources of the lumber, and this was a really good one for us because it kind of went out of the model a little bit because we had to do some research on our own, or Dylan did. So we contacted all the places where the material was coming from. Like, what is your sustainable harvesting practice? Tell me about it. And if there's kind of like, what? Then we moved on. But we want to SFI certified. So this one was a big one for us because this was the one we didn't know how it was going to come in. We love this West Coast lumber, and it comes from BC, British Columbia. And there's just so little waste. And we were really hoping that's where we should get our lumber. Even though it's from a long ways away, it's shipped by rail, it's shipped to Albany, and it's not that far from us. So, and the alternative is where most lumber yards in this area get their lumber is Eastern produced, Canada, and then Maine and Northeast United States. And so we thought maybe because it's coming by rail that the West Coast, and we're way less coal. We're using, we're not taking sorting lumber out. It was going to be a lot better. So we also went with our local suppliers and said, when the stuff we send back, this pile of stuff that we're not going to put in our walls, what do you guys do with it? And so we felt pretty confident they were telling us the truth. And they said we were able to resell most of it. So that felt good. So as it turns out, East Coast is better. It's just too far to get here from BC. And the final assembly was all cellulose, double stud wall. Now this is a tricky one because it gets into layout, but 19.2 on center. And so you got to really think out your assembly to eliminate waste on that. But with that, you can go 2 stories with 19.2 on 2 center. You can't go 2 foot on center, 2 stories. That's with double 2x4. So that's where we landed. So, okay, how do we build them? So we looked at, do we set up a factory? We set up a modular factory like some of our acquaintances have done? Or do we build it like Bucky Fuller and bring it in by helicopter? And that seemed a little excessive, but we love Bucky Fuller. So we basically broke it down into kind of a factory system on site primarily. There are components we'll bring into the buildings and put together, but that's how we broke it down. And we worked, and I'll get into this a little bit more. So the goal: dematerialize, build our buildings for passive survivability. That means the house is going to survive with or without solar panels, right? Make it resilient, the capacity of a building to retain and regain functionality in the face of distress, and bring in all our trade partners. And this is the key right here, is bring in all your trade partners to the table. That's where things get missed. We can have wall assemblies coming from really good factories who bring us, high performance walls. But if it's business as usual, when it lands on our site, we're going to have all of that inefficiency. So we want to look at waste. We want to figure out exactly what you need. We're going to give you replicable systems, but we don't want any waste stream at the end of the project, and we're going to help you get there. And the other thing that's really important is that we don't want anybody to lose their margins on the project. This isn't our goal for you to undercut anybody else. Keep your margins the same, mean how much you make off a project. But if you think it through, then we can reduce so much waste, and we're going to help you think it through. And that's what we've done the past several years, is work that. So what we developed was what we call East Branch homes. And basically, we take a simple facade and we reskin it. And You take a barn, you could have a barn, you could have a Gothic, you could have a modern. It's basically a similar shape that we can, it's replicable systems. We have different layouts that people can choose from. And we also have built systems that we can, as we know, being a builder for 40 years, we know how people move through their life, through their stages of being in buildings. So when that second bedroom, when the kids leave the home, we can make that those closets will come apart, break down, and they can become bookcases or different things of use in the house. So we want to think waste stream long term in our buildings. So we're not continuing to, when we renovate, to put things in the landfill. So this is the home we're building this spring. It's our first one actually, and it's our farmhouse, linear farmhouse is what we call it. So we also use local materials, so all of the siding is from Vermont. It's a bandsawn material. So we're really excited about it, but quite honestly, that wasn't the purpose of doing that, is to create another business model. What we really want to do is be better builders. We want to, from our trades to our company, and we have such an incredible resource and design in this area. From Kuhn Riddle Architects and C&H Architects and Laura Fitch and different folks. It's just like there's such a wealth of design capability here. That's what we want that fifth dial to be, is really strong design. That's where the success will be. And Carol, we're going to redo a project with Carol. So we don't want to be designers. We're not designers. We're builders. We just want to learn how to build more efficiently. And that was our journey to get there. So even if we never built an East Branch home, we would have learned so much in the process of getting there, and that was the intent to begin with. So we've got, for all you architects and builders and students, if you want a detail about a wall assembly you haven't done yet, shoot us an email. We'll send it over to you. If it can be built, we've probably put it together and we've probably drawn it. We've got a bunch. And there's some tricky details, and I think what happens without really good detailing and understand how things go together, it gets lost, is what we've seen. And that's what we got to fix in the building industry, is this design to build connection. And some of these details, how it really works, is tricky. And we're continuously refining how these things go together, because we want a continuous air barrier. That's got to work. And it's hard sometimes to make that work, especially in complex structures. So, we've got to really sit down at the table with design and with build and make sure we all understand how we're going to put this thing together. That said, we're not going to build our way out of this. This is a quote from the New Carbon Architecture, and this one just kind of hit home. New buildings are great, but man, we got a lot of stock we got to fix in this New England. And how do we do that is even harder than how we get affordable net zero. First place we send folks, Mass Save. Just get an audit, get that work done. It's low-hanging fruit. It's free. It's the incredible program that Massachusetts has. The other thing we're missing, I think, is opportunities. Is when we go into a home, like we want to put an addition on, we want to redo our kitchen, we want to fix our bath. What's the opportunity to make that house better? That I think we're missing in an industry. And how do you look at the possibilities of a house? And I'll dig into that a little further. And so when we meet with all our trade contractors, when they go to jobs, we say, just look around at the house. Looks like they're getting, they're going to need a new roof soon. Or you go up in the attic and you see, man, that's just bad. How do we fix this? And if we've got not just our eyes on it, but insulators, drywallers, concrete, everybody looking at this stuff, then, hey, when you replace that roof, why don't you put 4 inches of polyiso, seal it up? It's not that much more just to do that work. You're right there. Oh man, those windows, that siding is junk. It's falling apart, and the great thing is we got a lot of this work out there that we can do. New England has these beautiful historic homes and homes that aren't that great also. And some of the real beautiful historic homes are harder, more challenging, but that just makes it more interesting. And then we really look at a phased energy retrofit approach. That's key, I think, is that a big full energy retrofit is hard. It takes a while, it's expensive. But if folks can look at their house in progression of being fixed, of becoming energy efficient, then there's a sense of we can do this. Our house can get there. We may not be the ones to get it there. It may be the next buyer. It may be the next. But when we sell the house, we can give them this plan. We can say, I'll show you in a second here. So anyway, this is some of the things we analyze when we do a phased energy retrofit. We also want to start with, you have water in your basement, because we don't want to seal up this house if you got standing water and put all that moisture in your house. We have to have a way to dry this building out too. So when we look at the phased approach, then we can just look at attacking it a facade at a time and just coming in, doing it quickly. And so it's much less invasive to the house. We can just get it outside done very fast. So there's also an area between the mass save work and the full retrofit that's a few $1,000s, not tens of thousands of dollars. And so that's what we're also focusing on, is how do we fix that next level after mass save that makes another big impact before you get into full retrofit. So that's also what we're working on. But when we take this approach of kind of looking at how we're going to attack a building, we want to get it done fast. We want to get it done efficiently. And so we're going to get it like this building. So when you tie around the corner, it may look a little odd for a while until you're ready to do the next phase, but that front is done and it's energy efficient. It's airtight on that face. So it's having a full plan. And I'm not just blowing smoke here. This is my house. Somehow I got my wife to marry me and move into this with me. We very much took the phased retrofit approach, right? We had a lot of challenges in this building. It was an old grist mill from 1850. We had a little water intrusion issue we had to think about. So that was a challenge. How do you build a building that super insulated, airtight, and it can be submerged underwater for hours or days? So that was a challenge. And so we very much took a phased retrofit approach to it, and not get too worried about. I mean, I'm a builder, and people drive by and say, he's a builder. Of course it doesn't. It's not going to look done. So I had that going for me, but we got there. It's done. It's super efficient. It's fun to live in, and it's all that good stuff. I want to talk a bit about another really important book that came out a couple of years ago to me and my wife, Lynn, is Drawdown. And the thing I want to go back to is the hydrofluorocarbon, because again, this is thousands of GWP as compared to other refrigerants. And so this is one I just would like everybody to be aware of as you all going out into the world of building industry, is the stuff that we're using that's really bad environmentally. And the problem is it's on a scale that is going to just keep growing as the earth gets hotter and more air conditioning is going to come online. And how do we move away from hydrofluorocarbon? So I've been talking with Mitsubishi, the headquarters of Mitsubishi, and just through different channels that I was just happened to get to somebody who actually knew something. It's going to be a while. Eventually it may get to CO2 based, but that's a whole remanufacturing process. But they're going to move toward what's operating refrigerant now is called R14A. They're going to go to an R466A, which is about 65% less GWP than what's existing now. But we can push, and states can mandate this. So we're looking into what is Massachusetts doing around this right now? How fast can we push this? Unfortunately, you can't put this new refrigerant in existing systems. So that's off the table. And we don't know how fast this is going to change. But in this book Drawdown, it's the number one thing. If we change, we could make a huge impact on greenhouse gas emissions. So it's just something to be aware of, is that, is the refrigerants are that big of an issue. There's great resources. Green Building Advisor, the next to the Embodied Carbon Network and the Carbon Leadership Forum are great resources if you really want to dig into carbon. And that's the next big thing is carbon. We've got the energy efficiency dialed in. We really need to focus on embodied carbon. So those are two. There's very little chatter. It's really good information that flows through these forums. Some of those forums are terrible. These aren't. And then Building Green, which is based out of Brattleboro, Alex Wilson and Nadav are the owners and editors of this magazine. This is a great publication. If you really want to dig into materials, this is a great resource. And finally, it's how do we make what we do continuously to improve what we do. And it's about collaboration. We have such an incredible resource in Western Massachusetts and New England, from Maine to Connecticut, and all of the great work that's being done in design and building and technology and renewables. And how do we collaborate? If we're all kind of doing this on our own, then we're not going to move as fast. And we got to move fast on this stuff, right? We have to collaborate. We have to share what we know. There's no time to keep secrets. If we share what we know with other builders, then they're going to get better. That's going to make us better. That's the way it works. So we can't be afraid to share the things we learn. We need to be collaborative. We got to be creative. Like, that's just, and you folks going out there, you're going into a great world of figuring a lot of stuff out, and it's exciting. And, I see just in the past few years how quickly technology has changed around how we build, and it's moving all the time. This community we have around high performance building, again, is just amazing. And we can come together as a community. And being from Oklahoma, I can tell you this is a pretty cool place to be. It was a sigh of relief when we come back from that part of the country, and the community around that gets it, that wants to fix these things, that wants to make this earth habitable, is really cool and exciting. And the last thing is flexible thinking or flexibility. And this is the big one for me, because I think too often we get in a certain mode, like Passivhaus is it, living building challenge, that's it, that's all I'm going to do. LEED certified, man, that's the way to go. All of that stuff, there's all great stuff in all of those things, but when we get so keyed in on one thing, then we miss a lot of other opportunities. And we have to be ready to completely change, throw out the window what we thought was going to work is the best thing. Like, we're seeing data all the time. Like, we spent years developing East Branch homes, and we're thinking, you know what? Single family dwellings is not really what we should be doing. We should be building multifamily dwellings, that it costs less. We can make it more efficient. We can turn all of these dials up to 9 instead of 8 or 7. We can make this work. And there's an article that is just great to this program this morning, the New York Times, about California. It's, transportation is 40% of their carbon emissions now. It's terrible. Like, and this is a state that's on the cutting edge of making, addressing greenhouse gas emissions. But what's happening is they're losing their communities, and people are having to travel further out to be able to afford to live and work in the places they are. So we're not only taking up farmland, precious farmland that we're going to need, and building these, subdivisions. It's just, we have to change the zoning is a part of it too. So they're talking about even the state being able to override the local zoning restrictions on multifamily housing, so that houses can be built, multifamily can be built at least 5 stories, because that's where the work is, that's where the services are, that's where, you don't have to drive for miles and miles, 3 hours driving to get to work. So the flexible thinking is key, I think. And it's, when you do research, is to look at it from every direction you possibly can. I'm even in discussion now with folks that don't think CO2 is that bad in the atmosphere, because I want to hear what they have to say. I want to understand their point of view. I don't agree with them, but I want to hear that part of the puzzle. And it's, when you take in all of the information, you're just going to make a very informed decision, and it's going to lead you down a path to get us where we need to go faster. And I will tell you, by the quality of folks that have come to our company through UMass, through the Mass CEC program, is you're all in a great place to be learning this. And thank you.
Wait just a second, the much coveted BCT water bottle. Thanks a lot, everybody.